Please let me recall what is going on. So we're proving this proposition. We are having an arbitrary algebraic group G, an arbitrary subgroup, only up to this restriction that we agree that we can assume that L is Zariski dense in G upon replacing G with a restricted closure. So G is algebraic, L is arbitrary in it, and we are looking to find of some normal subgroup now in G such that L is precompact modulo H. L does not need to contain H. Mod H, it should be precompact, and we will have this property that whenever we find an L invariant measure, this is the main part, whenever we find an L invariant measure on an algebraic variety, it will be supported on the fixed point. And by the way, on the fixed point, of course, L act through its image mod H. So one can view mu, actually on this, if you replace V by the H fixed point, this is G mod H variety. G mod H acts on it. L acts through its quotient. Mu is L fixed, so actually it will be fixed by the closure of L as well. Stabilizers of measures are always closed, and this is a compact group. This mu eventually will become some measure which is invariant under some compact group action. This is something. Yes, I will. So, in the last talk, I gave an example of a situation that we don't have any invariant measures, and I remarked about another example. Obviously, for compact measure, we do have invariant measures on algebraic variety. For SON, we do have the Haar measures or the Lebesgue measures on the spheres. These are balls. These are invariant probability measures for SON. Compact measures have Haar measures on them, so they have many invariant measures. You cannot exclude that. This proposition says Haar measures are the only sources of measures, or of invariance. Obviously, we have many measures on varieties, but invariance phenomena you have only after some obvious reduction, and this is the technical part of the theorem. After some obvious reductions, invariance of measure you can find only because of the phenomena of Haar measures on compact sets, on compact groups. So this is the theorem, and so how we proceed to prove it? We focused on the L, and we look at all. First of all, G-homogeneous varieties, G mod H's, that support invariant measures. And we took something with smallest possible stabilizer. This is our H, or if you want, as big as possible G mod H that we can, and that still supports a measure, and an invariant measure. And so we focused on that H, and we claimed successfully that H is actually normal in G. Okay, so here we are, and now recall mu is a measure again on this group variety, which is L fixed. Let's just. I don't want at this stage of the theorem to say, okay, now replace, say, just G is G mod H. I don't want to be so confusing, but this is what in my mind. This is a group. I think now of this as my main group, and so let L. Okay, just wait. So G mod H acts on this variety. The action of G is via G mod H. The action of L is via its projection to G mod H. And the stabilizer of mu is
so
on.
Mu is not the mu from the proposition.
It is.
Right?
It is. No, it is the mu from was chosen right here.
Okay. But you are from
the proposition is about some arbitrary mu that I will have to address.
Okay.
Maybe I should have taken a different symbol, but
So mu is a proposition is quantified, it's universal.
yes. And then this was chosen. This is a specific one. Maybe. Okay. Now this mu is fixed under the image of L in G mod H, so it's fixed also under the closure. So let L bar denote not the closure of L, denotes but the closure of L, the closure of the image of L under the natural homomorphism to G mod H. Okay. Just slight interpretation maybe. Mu, agree, is L bar fixed. Now, L bar is a closed subgroup of the group G mod H, and it acts on it by left action. So, the left action of this closed subgroup L bar of the topological group G mod H, and this one is tamed. Orbits are closed. When we consider an action of a subgroup on a coset space, it might be when we consider, I don't know, the action of U on G mod gamma, for some previously explained notation, the orbits might be violent. But the orbits of a subgroup on a group are nice. We have a nice space of orbits. It's the coset space of that group or that subgroup, right? In particular, it is tame. The measure mu, this integrates again into measures supported on fibers. Fibers are just cosets of L bar. Fixed action measures. Mu pi. L invariant on a coset, or L bar invariant on the coset of L bar. Now, a coset by shifting is just isomorphic. The coset, comma mu pi, is L bar isomorphic to L bar itself. So by right action of G mod H on the coset space, on the left L bar coset space, I can take this coset space into the group L bar itself. To L bar itself with an invariant probability. Measurement. bar supports an invariant probability measure. This forces L bar to be compact. So this is a fact that you should know it's part of the theory of measures on group. On locally compact group, we have measures and invariant measures. There will be probability measures if and only if the group is compact. This forces L bar to be compact. Or that is L as a pre-compact image mod H. Okay? Let me say one more word here about, I think probably you all followed this. I was missing a single line if you happen not to think about C but about other fields. If you are interested, say, with CP, which is another field I might considering here, I want to add one more line. I will not write it down. Say CP. C is a locally compact field, but there are fields fitting into this theory, into our assumptions.
What is CP?
The completion of the algebraic closure of the p-adics. I discussed this briefly in the past. So I did not assume that this group L is locally compact anywhere. My variety need not be locally compact in fact.
But is not CP isomorphic to C?
No.
It is isomorphic, but not topologically. It is isomorphic as an absolute field. It is not locally compact field, but so it doesn't appear in this discussion. I mean, the spaces, I have spaces with these measures on them, and the spaces are Polish. I didn't use the fact that they are locally compact in any place. So one should add one about L bar. One should add that if a group supports an invariant measure, actually an invariant measure class, this is a theorem by Weil, it must be locally compact. L bar is locally compact and in fact compact. In particular, if a group supports an invariant probability measure, it is compact. This fact, this one by itself is not so hard to prove. I will not prove it here, but I want to make this remark. Over C, my remarks here are not important in any case. Everything is locally compact, and if you care only about the situation, then don't bother with that. Okay, I'm still proving. Where are we? We have seen now that this normal sub of H indeed is a normal algebraic, and L is pre-compact modulo it. That's fine. I need also to finish this. Now I need to look at this quantified statement. I needed to show that for every action and for every measure, this is the case. Of course, using this minimality. Okay? So now let me maybe make the following claim. This is like almost proving this claim. Let G act on V algebraic. Assume that we don't have any H fixed point. H was already chosen. Now H is a well-defined element in our consideration. Then the claim says that this condition could not be satisfied. So we expect to prove this follows from if you believe the proposition, but actually this is the core. This is enough to complete the proposition. So let me start by this reduction, this claim. Proof of claim. The trick would be again to take take mu naught on probe V. I'm arguing against by induction. And I will multiply it with G mod H comma mu, and by this I will force reduction of the stabilizers. Consider the measure mu, this is my fixed mu, times mu naught in probe G mod H times V, and this is indeed L invariant. And again, this integrate this it with respect to the G action. So it is integrating it over the space of orbits, which is nice. I'm repeating this trick again and again. It's taking product, disintegrating, etc. Get a measure, I don't know, mu prime prime on an orbit. G mod H prime. I use that, H prime prime. Did I use H prime? Probably yes. No? Mu1, H1, this was not here. Okay. On an orbit, which is isomorphic, to G mod H1, L invariant. Check that after conjugation, H1 is slightly smaller than H. So what is H1 again? Maybe it's the intersection of a conjugation of H on one hand and something else on the other hand. This something else does not contain H because of this is something. When I intersect H or conjugation of H, well, H is normal. Forget conjugation of H. When I intersect H with a group here which is not H fixed, I'm getting something which is strictly smaller than H. Right? And I just got an invariant measure on this. This contradicts the minimality of H. A smaller subgroup cannot support an analytic line. Okay, after having this claim, to complete the proof is rather easy. Now fix now any algebraic action G on V. And mu an L invariant probability on V. If mu of the fixed point H is not 1, restrict to the open set to V minus VH and normalize mu to an L invariant probability measure on contradicting the last claim.
Why is VH invariant?
Sorry?
Why
H is normal.
H is normal.
It is VH is G invariant actually.
H is normal.
Okay. So by this I show that by this I show that for every V and every invariant measure on it, every such is supported on the H response. And this is the end of this proposition. And so again, we do have invariant measures on algebraic varieties under groups, but always because of trivial phenomena. Either because these invariant measures are actually supported on fixed sets of things, or because of compound groups, existence of compound groups. And this actually forces, the claim is that the next claim, which will be very, very important in the next days, improving Maruli superrigidity that I want to do, will involve weak mixing. So I discussed previously measures which are not only ergodic but doubly ergodic. Assume you have a probability measure such that its square is ergodic. Maybe before proceeding and injecting a new ideas into this, let's step back, forget algebraic geometry, and just regard compound groups, and say something about doubly ergodic measure. So observation. Let K be a compound group. Let X be a K the backspace. Let mu be a measure on X, or an invariant. Okay, invariant. Measure on X. Assume that mu cross mu is ergodic on X plus X. What I want to say, this cannot happen. I mean, of course it can happen if I take a delta measure on a fixed point. This is the only way. Then mu is a delta measure. Dirac measure on a K fixed point. So this is well, observation, lemma, I don't know how to call it. In my notes it appears inside a certain proof that I'm about to present, but maybe I decided right now to separate it. This is a general claim, and somehow I'm about to encode this into a proof saying that also you don't have such measures, doubly ergodic measures, for algebraic varieties, unless they are delta measures. This will come as a corollary of this.
You could prove more if K is compact and every ergodic measure is
So first of all, an observation, which I was supposed to state at some point, and I haven't. K compact implies every ergodic measure is supported Why is that? Well, I was brief here in the formulation. K compact and it acts on a certain space, blah blah blah, and a backspace. As I said before, every action, every Lebesgue action could be made continuous. So whenever I'm acting, I can actually replace my space with a continuous action of this compact group on a topological compact metrizable space. And then, as we know, we have nice orbit structure. The action is proper, the orbits are closed, etc., 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 and I can disintegrate, or I can push the measure into the orbit space, and this will be must be a delta measure, an invariant 0-1 measure on the orbit space, which must be a delta measure. So this means that my ergodic measure was supported on one orbit. So for the lemma, to prove the lemma, actually, need to consider mu, which is a probability measure on some orbit, K mod M.
Let me ask one thing.
Yes, please.
This double ergodicity is stronger as we mix it.
For invariant measure, double ergodicity is equivalent to weak mixing, as we've seen. Yes, this.
And then you can apply Peter Wright.
I can apply Peter Wright. To prove the lemma, we need to consider measures. I mean, if mu is doubly ergodic, obviously it is ergodic as well. So, so it is a measure on a certain space, but this space could be replaced by one orbit, K mod M. M is some generic stabilizer, which I don't know yet. Actually, I want to show that M is K, that my orbit is a point. And this is K invariant. But there is a unique such guy. Mu is the unique invariant measure on that compact space. For any compact action, a compact homogeneous action, you have a unique invariant measure. And it is fully supported. Mu cross mu now, again, is fully supported on K mod N times K mod N on one hand. But by ergodicity, again, we consider ergodicity of the diagonal action. It is supported on a single orbit. These forces that the whole situation is stabilized. Okay? So these two boards represent a phenomena very familiar and very easy to prove, as we see, for compact groups. But the proposition, no, I did plan it well. The proposition appears here, says exactly that, in some sense, invariant measure under algebraic varieties, the theory of is reduced to the theory of compact actions. In a sense. So this is the corollary.
Could you repeat the last sentence?
Yeah, I mean, it's not mathematics, it's just the proposition here basically says that the theory of invariant measure under group action and algebraic varieties reduces to the theory of compact group, or measure invariant under compact groups, in a sense. So this is what I want to explain now. I mean, I want to write down an analog of this lemma in the setting above, and this will be a very useful observation. Maybe I'll give a title theorem for this, but now it's on the level of observation. This observation that follows from theorems called corollaries. I'm in the setting of the proposition. So I'm having this, I'm having that, I'm having this, and now assume mu times mu on the is L ergodic measure on V times V, then mu is some delta measure for some V in V, which of course must be L fixed. So I just have to collect. So let me take some cool shortcuts. So first of all this claim has nothing to do with G. Everything is happening in the everything is happening in the Zariski closure of it. And second, well, I'm using the proposition, so I will use the letter H now, without introducing. It's the one that comes from the proposition for that setting, and the measure mu is supported on the H fixed points, right? Nothing is happening in this business outside the H fixed point, so we may assume that V is the H fixed point, right? Further, on the space of H fixed point, the action of G is via G mod H. H is normal because of this assumption. H is normal in G, and the action here is of H is trivial, so I may assume now that G is G mod H. And four, I'm considering now the image of L in G mod H, which is precompact, and what I would assume is that mu is L fixed, but also mu is fixed under the closure of L, and this assumption that mu times mu is L ergodic, so obviously mu times mu will be L bar ergodic. So I can assume L is compact. So these are the reduction that the situation allows me. Well, I guess so. Now the previous lemma applies a corner. We are in good. So this is what I wanted very much to do. Let me state now.
Wait, for this reduction, you
So-
just say that L is acting trivially on V.
No, I didn't say that L is acting trivially on G. No.
No, you did it. You did it, okay.
No, but L is discrete.
Okay.
Now, let me state a specific specialization of this corollary. Maybe I'll write it as an example, but this one I will use in the future. So we should bear this in mind. Now take G to be SLLC. I will use it for SS3 when I prove rigidity. And it acts on V, algebraic action. Take S to be SLR. And gamma Elatus. Oh, sorry. Sorry. Excuse me, I got confused with my notes. S is SS3R, H in S non-compact, G any algebraic group, maybe over a different field. Write it. And H to G, some continuous homomorphism. Sorry, I was heading ahead of myself. I was trying to rush and didn't present some notation, so forget this. There is something that I do want to present very briefly before sending you guys away this time, and maybe I will write a term. The proof is now very easy, given what we have. And it's actually this term that I want to present before the ending today's lecture is just a generalization following what we have of what we had at the very beginning of this. I'll do it more. Okay.
So in all the things that happened today, you assume that the field over which you are working is just complete and not necessarily algebraically closed.
I did assume that the field is algebraically closed on one hand, and also I assume that there is evaluation on it with respect to which the field is complete. Okay. So I set some general theorems. What I want to do now, very briefly, and I will do it as an appetizer at the beginning of the next talk, is just formulate a generalization of this little exercise about SL2Z invariance maps from R2 to R2. If you remember, we spent about 2 hours proving it, basically introducing some techniques. But now we have the tools to do it in a much wider generality. So, but I will be very brief about it because we've seen everything. We just have to collect things together. And the next thing I will start to do is considering what we call an algebraic representation of ergodic actions. This theory that we developed with Alex Foreman about representing measure space as algebraic varieties, and the first technical steps we already done. I mean, the main technical steps. And this corollary, so I want to welcome this corollary in another language that will serve me for next time. I will not do it now, but we should then remember this corollary. Probably I will restate it. But we don't have weak mixing measures on algebraic one. This is something to remember.
May I ask one more? Where being algebraically close place zero, which part was
So I did mention it plays a significant role in the proof I gave of tameness of actions. In fact, one can improve the results. I did not do it here. One can have, all this discussion is actually correct over an arbitrary complete field. Complete field with absolute value. But then, constructibility of actions should be reproved. And for this, one needs to introduce analytic geometry. I mean, not only algebraic geometry, and this I haven't done. If anyone is really interested in this subject, I gave a course about it at the Technion, and it was videoed. So one can look up for videos. I explained everything, not in positive characteristic. Actually, it holds also for any characteristic. In my explanation there, even I didn't discuss to full extent positive characteristic. But again, what I'm saying here does not need algebraic closeness as an assumption. But then my proofs are just not complete, and I want to present complete proofs. And this is enough for most applications.
Just one last slide.